Good day, everyone. For this video, we'll be discussing about physical properties of fuels. The first physical property of fuel would be our density. So every stuff has a density, whether it is solid, liquid, or gas. So simply put into context, every matter has density because it has mass and it occupies space or has volume. The fuel oil density is an important characteristic that shows a fuel's ignition quality and is also used to calculate the amount of fuel oil provided during the bunkering operation. So take note, density is important since we will be using it in solving for our fuel consumption when we reach our higher engineering subjects. So for density, it changes with temperature. So meaning we need to have a common understanding that density changes with temperature. Thus, we need to take note of the temperature at which we we supply our fuel to our tanks in order for us not to be not to lose money because of incorrect judgment and at the same time incorrect calculations. So density is equal to mass over volume. This is our formula on how to solve for your density of a material. Simply that's mass divided by the volume. So density is vital for determining the weight of fuel per unit volume. It influences storage and transportation logistics, ensuring vessels can carry an optimal amount of fuel without compromising stability. This is what I mean earlier, that density is important in solving fuel consumption, since without density, then or without understanding the density of a material, then we might have errors in our calculation, especially in terms of temperature reading and the density of our fuel during the bunkering operation. The next property of fuel would be our viscosity. Viscosity is the fluid resistance that operates against the flow. So this is internal friction. That means our fuel will have a tendency not to move fast or to move slow because of its viscosity. Kinematic viscosity is a measure of a fluid's dynamic viscosity per unit density. So this is another type of viscosity, which is your kinematic viscosity. We simply divide our dynamic viscosity with density. The viscosity of the fuel is an important characteristic since it determines the ease of atomization and the ease at which the fuel can be pumped throughout the system. So there's two things that you need to understand here. Atomization, or wherein we have a nozzle where we can actually make our fuel into droplets. So depending on its viscosity, it could actually burn easily or burn slowly because of the formation of bubbles through the nozzle. Next, pumping system. So generally speaking, when we have higher viscosity, there will be a required pressure that is also of higher amount as compared to pumping a particular fluid or liquid that is actually of low viscosity. So here, viscosity and pump. The viscosity of the pump fluid also impacts the net positive inlet pressure required, or the NIPR, and the input power of positive displacement pumps. Theoretical horsepower is proportional to speed and pressure. Friction losses due to the viscosity of the pump fluid cause the input power to increase above the theoretical power. So viscosity adds up to the friction, and then it also adds up to the pressure requirement of our pump. So particularly in this particular diagram, we can see that as we have higher viscosity, our inlet pressure required is also higher. And here on our second line, we can see here that with lower viscosity, our inlet pressure required is also lower. Therefore, they are directly proportional with one another. Viscosity or fluid resistance impacts the ease of fuel flow, as with what we mentioned, because of pumping system. In marine applications, it's essential for efficient pumping and atomization, affecting combustion efficiency and overall engine performance. In terms of atomization, we need to understand that as we increase the surface area of contact, meaning we atomize our fuels, there will be actually higher combustion efficiency. But if there is like lower atomization because of higher viscosity fuel that we use, then therefore there will be also problems in terms of our combustion. Specific gravity. Specific gravity indicates the density of fuel relative to the density of water. Take note, this water here should be fresh water at 4 degrees Celsius. It's essential for assessing buoyancy, stability, and the volume of fuel needed to achieve desired energy output on a vessel. So for the formula of specific gravity, we have here density of the object divided by the density of the fluid. In this case, it's always fresh water at 4 degrees Celsius. Now, we have here what you call as the American Petroleum Institute gravity or the API gravity. It is a measure used to quantify the relative density of a crude oil and other liquid petroleum products. Relative, meaning we have two liquids which we base this particular measurement. It provides insights into the oil's composition and characteristics. The API gravity scale is inversely related to the density of the liquid. Take note, inversely, meaning as we have higher API gravity values, these indicate lighter and less dense liquids. Again, as you go up or as we have higher API, we have lower density. So if there's lower density, the tendency of that particular material will be to float in water because our reference for API is also water, while lower values indicate heavier and more dense liquid. What do I mean? As we decrease our API gravity reading, our density tends to become high, meaning it will sink in water. Crude oils with API gravity above 10 are considered light. Those between 10 and 20 are classified as intermediate, and values below 10 represent heavy crude oils. So as you can see here, the pattern, if we have above 10, higher API, our density is light, meaning lower density. Those between 10 to 20 are considered intermediate. And for the last statement, as we decrease the value below 10, our crude oil becomes heavy. So therefore, the density is higher. So this is our diagram from Engineering Toolbox. As you can see here, as you increase your API, your specific gravity decreases. But once you have lower API, your density increases. Therefore, API and specific gravity are inverse proportion. As one goes up, the other goes down. Remember that. Flash point. Flash point is the temperature at which the vapor of heated fuel ignites. Remember, this is the heated fuel. You heat the fuel and then the vapor will automatically ignite at this particular temperature, and you call this as your flash point. This is done using a test flame under certain test circumstances. According to SOLAS, the flash point for all heavy fuel oil used on board boats is established at Penske Martin's closed cup 60 degrees Celsius. So flash point is important for the following reason. Flash point is important for handling and storage to prevent accidental fires, ensuring safety during bunkering, storage, and engine operations. We don't like to have accidents or incidents of fire on our vessel as much as possible. So in terms of storage, we need to make sure that our fuels is securely stored in a vessel and that once we operate our fuel, it will not easily ignite at lower temperature or else we will be catching fire in our vessel. Next, cloud point. Cloud point is for distillate fuels and is the measure of the temperature at which clear distillate fuel becomes cloudy due to the formation of wax crystals. Take note, this is because of the wax crystals formed in this particular fuel. Compliance with the parameter ensures that the fuel is suitable for use in ambient temperatures, down to negative 15 degrees Celsius without heating the fuel. So as much as possible, we don't like this formation of wax at lower temperature because it will actually clog our system. At the same time, it will increase the viscosity of our fuels. And once we increase the viscosity of our fuels, there will be problem with combustion and atomization processes. So cloud point, we should avoid it, or we should have a cloud point up to negative 15 degrees Celsius or lower than negative 15 degrees Celsius. In cold marine environments, understanding these properties is vital to prevent wax precipitation, which could clog fuel filters, as what I mentioned earlier, and affect engine performance. Pour point. The pour point is the temperature at which the gasoline stops flowing, or your fuel stops flowing. When the temperature of the fuel oil falls below the pour point, wax develops, just like your cloud point, which can cause the filter to get clogged. And you don't like this to happen, especially when you forgot to heat your fuel during your operation. So in order to answer this issue, pour point or the pour point in order to remove the wax formation of crystals, then therefore we need to heat our fuel, which actually means additional cost and at the same time additional process in our operation. The wax deposit will also accumulate on tank bottoms and heating coils, reducing our heat exchanging capacity. So in cold conditions, especially during Arctic or polar voyages, knowing the pour point is essential to prevent fuel solidification, just like what happened here, and ensure continuous fuel supply to engines. Because there will be time where we already hit our engine for the possible entry of fuels, but because of the formation of cloud point or formation of pour point due to wax formation, then therefore we cannot easily burn or ignite our fuel because of this particular physical property. That's it for the physical properties of fuel. I hope you learned something and see you our next video. Bye bye.